Okay, we are live now. So let's start. Hello, everyone, and welcome to this another session at Reactive Summit. Let me share my screen and welcome over today's talk. Okay, so today we're going to be talking about RSocket over QUIC. And this is going to be like not a showcase that RSocket can work over QUIC. Of course it can. This is going to be a tale of how we made, or almost made, because this is still in progress and everything is still in incubation, but how we made RSocket working over QUIC and what we had to change in different layers used in RSocket, in React Netty, in Netty, and in order to have QUIC in Java, what happened in order to make all of that. So first of all, let us introduce ourselves. Today we have a great person, Violeta. Violeta is a main. It's a leader. It's a leader of React Netty project. She's a contributor and committer to great project Netty, and she knows everything about networking, network stack, high performance communication over network using Netty, and so forth and so on. Violeta, did I miss anything on what you do?
No, that's all. Thanks.
And my name is Oleg. I'm part of Project Reactor team. It's my honor to work with Violeta in the same Reactor team. But I'm working on the core, kind of on the Project Reactor, which is a great library for building and bringing great reactive, functional, declarative API for masses. And of course, one of the APIs that you can get and start using through React Netty is Project Reactor, which gives you fluxes and monos. But this talk is not about this. This talk is about RSocket. So first of all, I'd like to remind you that this conversation is not about RSocket basics. If you want to learn more about RSocket, like the ground, the base of RSocket, I recommend you to go for Sprint 1 and find Sprint 1 of this year, and find our keynote with Rosen Stoyanchev about RSocket, the future protocol. Or there is a ton of other videos at the YouTube. So I recommend you, if you have never heard and learned about RSocket before, I recommend you to look at this content first. Today we're going to be talking about really deep stuff about the design of RSocket, the internals, the architecture, the protocol bits. But anyways, I'd like to give you a short recap of what RSocket, just to touch the base, so you remember what it is. So RSocket is open source layer 5, layer 6 protocol. So it's like similar to WebSocket. It's session oriented protocol. The main feature, the key feature of RSocket is that it's Reactive Streams semantic-based protocol. So Reactive Streams is a protocol which brings proper messaging semantic, streaming semantic, and backpressure semantic, which enables like resilience. RSocket just copy that, transform into network messages, into packets, into frames, and that's it. So you get all the things that you get with Reactive Streams, but in the network protocol, and you can just transparently message between your microservices. Not only with just streaming semantic, it gives you much more to that, like just normal request response. It gives you much more like advanced resilience. And of course, one of the key feature is performance. That's why we wanna research QUIC, because QUIC is given performance as well. So RSocket has tons of feature beyond just streaming and Reactive Streams. It has peer-to-peer communication, request response, flow control, resumability, fragmentation, extensibility. It's just network protocol, so you can send any binary messaging in any messaging style, including RPC or just event sourcing if you wish. And it has many implementation in different platforms. But another key feature is that RSocket can run on top of almost any transport you can imagine, binary transport, of course. So it can run on top of TCP, WebSocket, or Aaron. And today, as you may understand, we wanna look how RSocket gonna be running over QUIC. So we want to implement that, and we want to see how it was done and what changed. But yeah, step by step. So in order to get to QUIC in RSocket, we have to go through another parse related to learning QUIC, related to learning Netty project, which is basically the top framework, top asynchronous messaging framework and network framework in Java ecosystem. And we want to see how it was finally all adopted in Reactor Netty. So Violeta, can you help us with that? Can you explain all these beats? Can you explain all the challenges that you absorbed and that you solved in order to make all this working in Reactor Netty as a main key tool for RSocket?
Okay, let me start with QUIC. In addition to QUIC, we'll talk a lot about TCP because we want to give you our perspective why we want a quick transport in Reactor Netty, in RSocket, etc. But before starting talking about QUIC, let's look at TCP. Because TCP actually was the domineering protocol so many years. So how the network stack looks like, we have TCP, whether we want to use a secure connection or not, we may have TLS. And then on top of that, we have an application level protocol. However, these days, the industry has requirements towards TCP protocol for a faster delivery of the data, for a security of the protocol. So it started to be very hard to answer to all those requirements that the industry has. And in order to be able to do something in that direction, here we have the new highly efficient and secure protocol. Maybe you've been hearing about QUIC since several years. How QUIC is based on UDP and how we may have another HTTP version of the HTTP protocol. And actually, it is a fact. This year, the QUIC RFC was finalized and released, and we have it. We have the QUIC already finalized. But before continuing with what QUIC gives us as an efficiency and security, let's look at TCP protocol. What, for example, we need in order to just establish a connection from the client to the server. Let's have here a client, and we want to establish a connection to the server. The very first thing that we need to do is the well-known three-ways handshakes, like SYN, SYNAC, and ACK. And with this establishment of the connection, you already have one network round trip. And here we actually didn't have encrypted connection. We didn't configure any security for that connection. You know that the security these days is so important. So what we need in addition to do in order to have a secure connection, we need to do a TLS handshake. And with the previous TLS versions, you need to make several network round trips in order to do these TLS handshakes. Like exchanging the certificate, set up the handshake, etc. But in this talk, let's talk only for the latest version of TOS, which is 1.3. And fortunately, with 1.3, we have only one round trip. So now, at that point, we are able to send the application data. So basically, we need at least 3 network round trips in order to receive the actual application data from the server. During the years, there were many attempts to solve the problem with the delivery and how fast the application data is delivered. Starting from for example, on the client side. On the client side, we have connection pool, and that's because we want to establish the connection once. And in order to save this first round trip, we reuse this connection for many requests after that. However, these days we have so many network components between the client and the server. So yeah, you can imagine that some of them might decide to close the connection because, for example, some idle timeout or something else. So actually, connection pool helps, but you still might face a situation where a connection is closed, you need to establish again a connection to the remote peer. CDNs were introduced. What is a CDN? Geographically distributed servers that works together in order to provide the application data faster. A new version of the HTTP protocol was introduced, HTTP2, in order to try to address how many connections are used when communicating with the server. However, all these attempts, none of them tried to do something on the protocol level, on the TCP protocol level. And now with QUIC, we actually are able to address this on the protocol level. So let's look how all these round trips look like from QUIC perspective. We mentioned that QUIC is UDP protocol based, UDP based. So naturally, the first round trip where we establish a connection, there is no such thing. We can remove that first round trip. Of course, the second round trip where we have TOS handshake, that's mandatory because QUIC cannot exist without security. And then we are able to send the data. So in comparison with TOS, we already saved one network round trip. But QUIC can provide more to this. For example, let's say that the client and the server have a recent communication between each other. Next slide, Oleh. So we are able even to remove the TLS handshake, and with the very first network round trip, we are able to send the application data. And this is the so-called zero RT or zero round trip time. So basically, we can speak a lot about QUIC. There are so many interesting things, how the congestion control is happens there, the loss detection, how the connection migration happens. But yeah, I don't think we have enough time in this session today. However, there is one interesting thing about messages, how they are handled, the ordering of the messages, etc. And this additional bit will touch later in the presentation when we discuss the RSocket and the different transports there. So Oleh already mentioned that RSocket is using reactor Netty / Netty. So what is Netty? Let me briefly introduce it. This is an asynchronous event-driven network application panel. And it actually hides the whole complexity that you have in the network programming. You do not need to work directly with sockets, for example. Or if your particular solution needs different transports, imagine that one solution may need NIO, the other EPO. All these different transports, they are provided by Netty, so you do not need to worry about them and implement them, etc. It is highly extensible. What this means? Of course, Netty comes with implementations for the well-known protocols like HTTP, WebSocket, etc. But imagine that you have another protocol where for which you do not have an implementation provided by Netty, or you have your own protocol. For these use cases, you have extension points, and you can use them and actually provide your own implementation on top of Netty. What kind of quick support we have in Netty? As Oleh touched this, we actually do not have anything in Java about that. The Netty maintainers decided to utilize QUIC as an implementation for the QUIC protocol. And on top of that, they provided a QUIC codec so that you can create and configure a server and a client and start the communication between them. Of course, depending on the platform where you want to use these, there are binaries for Linux or macOS or Windows. One thing that I want to mention here is that this support is still in incubation phase. So you should, or all of us should consider for the moment that the API is experimental and not stable. So what is reactor Netty? What can give you reactor Netty in addition on top of Netty? Reactor Netty is a project part of Project Reactor, and it gives you the necessary Reactive Streams bridge on top of Netty, so that you are able to use Reactive Streams API over Netty. In particular, this is Flux and Mono because Reactor Netty utilizes Reactor Core as Reactive Streams implementation. As a networking features, Reactor Netty does not add anything on top of Netty, but I said that Netty simplifies the complexity of the networking programming. Here, Reactor Netty simplifies the work with Netty and gives you a really simple and very easy to use way to configure and create your servers and clients, and on top of that configures the needed codecs in the Netty pipeline and translates everything to Reactive Streams API. So basically, at the end, you are working only with Reactive Streams API. And last but not least, we have a built-in back pressure support. You will ask here, okay, if we have a built-in back pressure support in Reactor Netty, why do we need RSocket? And that's because RSocket actually propagates the back pressure through the network, which you cannot do with just Reactor Netty. In Reactor Netty, in the current stable versions, we provide builders for server and clients for different protocols that you might need, for example, UDP, TCP, or HTTP. And just recently, actually, we released an incubation project, QUIC support, which is again the same as the Netty support. This is an experimental. But yeah, we try to provide you the same experience that you have till now with UDP, TCP, and HTTP, but this time with QUIC. And now let's see whether it is really easy to create a QUIC server and client, or it's just me that is thinking like this. So let's first start with the QUIC server. What we need as a first step is to configure the bind address. Then we have to configure the desired security because we cannot work without security here with QUIC. Then we need to configure the desired limits for the data. For example, how much data you are allowed to receive or send, or how much streams are allowed to be opened by the client, etc. And then you bind the server and start waiting for a client to initiate communication with you. Here in this example, you can see one very simple IO handler that actually handles only the incoming streams. These are streams created by the client, and it just echoes the received message. But with the API that we provide, you are able also to open streams from the server to the client. Now let's see what we have for the QUIC client. At the beginning, we have to set up the QUIC client. In addition to the bind address, we need to configure the remote address. Again, the same as the server, we need to configure the security, some limitation for the incoming data, etc. And that's all. We connect, and once we are connected, we receive a QUIC connection. However, this QUIC connection is still not enough in order to start exchanging data with the server. We need to open a stream. But once we open a stream, we are actually ready to start sending or receiving data to the server and from the server. And that's just a brief touch about what we have as support for QUIC in Reactor Netty. Of course, we cannot touch a lot about behind the scenes, so this might be another talk. So let me hand over now to Oleh, who will explain us what we have in RSocket for QUIC.
Yeah, great. So first of all, we've seen that it was kind of challenging to support QUIC in the Netty because, as I understand, it requires like some GNI binding to C++ implementation. But at the same time, as far as I remember, you told me that like implementation of QUIC transport in Reactor Netty was almost as easy as pie, since you reuse like half of the functionalities that you had for HTTP2 and for just normal fluxes and the big pressure mechanic. So it looks like the implementation and port of QUIC in Netty was almost like smooth.
Yeah, that's true. We reused a lot of our abstractions in order to provide this support for this new protocol. And I'm really satisfied that actually we can prove that what we have as an abstraction in Reactor Netty you can easily reuse for implementing a new protocol.
So actually with RSocket, it should be like, at least it seemed to us as engineers of and maintainers of RSocket from protocol to the Java implementation and other language implementations, that support of quick transport should be even easier than in Reactor Netty, since we just have to use Reactor Netty and the greatest fluxes and monos from Reactor Netty, and that's it. And we're already using very much all of this API. But first of all, in order to get here, let's have a look at the general design of RSocket from the implementation perspective first, and then we're slightly going to look at how it is from the protocol as well. So on the RSocket level, we have like 3 main blocks in the design. It's RSocket API. It's basically what users are using every day. It's fluxes, monos, it's request stream, it's request channel, it's request response, fire and forget, or other type of invocations. And then they just uses fluxes or monos, depends on invocation type. Then we have protocol layer. And protocol layer is basically where all the magic happens, where all the engine just happens. It's including codecs, RSocket features like leasing resumability, and much more to that. And then we have transport layer, and the transport is basically duplex connection, which is basically a wrapper around just normal connection, and it looks pretty straightforward, since we send and receives fluxes of byte buffs. Byte buffs is a part of Netty API. We just reuses byte buffs for performance reason, and fluxes because Reactor Netty is already talking with us by using fluxes in mono, so we have just to send fluxes of outgoing data and receiving a flux of incoming data, and do the following. Basically, what we need to do is this: we need to multiplex and demultiplex. And you may say, why do we need to do that? Because beforehand, before QUIC, even including HTTP2, and from the point of RSocket protocol design, and it happened in 2014, everything that we had is basically TCP-based protocol, because HTTP2 is TCP-based protocol. That's why folks designed it like HTTP3, which is based on QUIC, and they had to change the version of HTTP yet another time, and we still have the same API, by the way. Without like, even we change the transports, we don't have to increment our API version. Anyways, we supported multiplexer and the multiplexer on the protocol or internals of our implementation, since all type of transports that we supported, basically, which was TCP, WebSocket, in memory, Aaron, was just connection oriented transports, and that was fine. And the other part was, of course, frames handler registry, which was like as closer to our internals as possible. And multiplexer could get access to frame handlers. The multiplexers could get access to frame handlers. Frame handlers could get access to multiplexer and the multiplexer, and like almost directly to flux, and send data into this single flux. So it was super easy. This is piece of code from our internals in Java. This is an example of frame handling from this incoming flux. So nothing really complex. What we've done here is just decoded our frame, taken stream ID, since it was encoded in the frame header in this byte buff, find out our frame handler, and then deliver it, depends on the frame type, what we need. So it was super easy. It was implemented almost inside the core engine, and yeah, nothing complex was there, and it just worked. And it worked like this. But the problem was that, like, the multiplexing, that it's not a problem. It's just a feature. Let's say the feature here was that everything was multiplexed. And since our connections that we support was just like a pipeline through which we have to offer our frames, like in the queue, we had to put them in like in the flux first, and then they sequentially had to go through that connection and then the multiplex. So even though frames are coming in parallel inside our engine, in any case they are sequential or like going sequentially through the connection, because that's how TCP-based connections and communication working. So connection-oriented sending. And that's what I just demonstrated. And that's exactly the first challenge that we faced during the new QUIC transport support. Because QUIC transport is absolutely different. If TCP-based communication guarantees that the frame A, which is going first, will be delivered first, and the frame B, which is going after, will be delivered after, with QUIC, it doesn't work, since frame A for stream AD1 maybe go first on the client side, and then frame B for the stream 2 going secondly. They can be delivered in absolutely different order. So frame B can get earlier and frame A later, or I don't know, frame A may get to the destination earlier than frame B. So it's first of all unpredictable, because QUIC doesn't guarantee the frame order on the full connection level. It guarantees that frame A for stream AD will end up at the destination earlier than frame B for the same stream AD, but not the other way. So if stream AD is not the same, then the ordering is absolutely unexpected, and because of that, we had problems in the building and supporting QUIC. And as Ben Christensen mentioned, the reason for having connection-oriented guarantee was to support resumption. So we wanted to somehow fix that. Actually, we redesigned resumability from scratch, and you may find a pull request on how we support new resumability 2.0 exactly tailored for QUIC. But nevertheless, once we fixed that, we started redesigning our internals, and what we figured out is that now we have a duplication of functionality. If before multiplexer and demultiplexer naturally sit inside RSocket internals, now multiplexer and demultiplexer in internals of RSocket engine, and multiplexer, demultiplexer, and registry inside QUIC protocol or QUIC connection are absolutely redundant, since in order to basically stream all the data from QUIC to RSocket, we have to do like double conversion. We need to get the multiplex stream, multiplex it into flux, since our API is just a flux of byte buffs. And then we have to demultiplex it again in order to deliver to a proper handler. So it's just insane, because this is double conversion. This is redundant work for sequentially and desequentially all the information. So this had to be fixed, and we start. Yeah, I put basically this slide in the wrong order. Apologize for that. Anyways, we started thinking on how to fix this problem, and we decided to put multiplexer, demultiplexer, and registry exactly on the duplex connection, because it naturally fits into this place. Since what we have at our socket level is basically streams. And of course, along with just multiplexer, demultiplexer, registry, we have frame handlers. Frame handlers are tailored for different type of streams. So request channel frame handler has one behaviors, request stream frame handler has another behaviors, request response and fire and forget, totally different beast to the previous. So all of those things are part of the engine. Along with that, we have codecs. Along with that, we have support for leasing, for resumability, and all this stuff just fits well on the protocol level, while multiplexer, demultiplexer, and registry sits well on the duplex connection level, because usually this is part of duplex connection. And we've seen that even with HTTP2, but we had no idea from the very beginning how to properly design that. So we removed all these bits from the core and put it into duplex connection. And now, for example, for QUIC, we don't have to, we have kind of out of the box support for all the things. So all our streams just naturally connect to the QUIC. For example, for TCP, what we could do and what we've done, we basically created adapter and we poured all of the engine that we had for multiplexer and demultiplexer from the core protocol to TCP. And now every duplex connection, if it's needed, has to request multiplexer and demultiplexer from the core engine, which knows some standard things. So we redesigned our interface to look like this. Instead of sending and receiving flux, we kind of encapsulated part of this logic into multiplexer and demultiplexer. Multiplexer and demultiplexer start look like this. So instead of just sending fluxes and receiving fluxes, we just tailored to support real streaming on the connection and multiplexer level. So for example, if we need to send something for connection, for service, for protocol communication, there is connection outbound and connection inbound handlers. Depends on what you want to do, handle or send. And then you have API for creating streams as well as for handling streams. And all these things are separate. And now our socket core logic just have to set up proper handlers and, for example, invoke or create particular frame handler depends on the incoming request type, which is great. So, for example, QUIC multiplexers started look like this. Once we got QUIC connection, we can just directly call from create request stream connection dot create stream, and once we got inbound and outbound, we can just supply to stream handler, which can send proper frame and listen for incoming data. And it's gonna be absolutely dependent on when this kind of stream gonna be closed, reopen. I don't know what can be done. Absolutely inside frame handler, and frame handler knows when to close and what to do with this particular stream. So stream is just a wire of frames, while particular request gonna know if, for example, it's request response, that after the first incoming frame, there is a need to close the stream, and we don't have to wait for other frames. So all this part now can be hidden inside frame handler, and this can be fully generalized since basically it doesn't matter whether it's TCP or QUIC. For example, for TCP-based transports or connections, we can just supply this type of client-server input multiplexer and demultiplexer, and then, of course, this logic that you've seen before will be inside the connection and inside this multiplexer and demultiplexer. But yeah, there is much more to that, but we don't have enough time. We have to summarize since we are running out of time, and we're 5 minutes or 7 minutes after the limit. Mm-hmm. So let me give a summary of what we just talked through. First of all, we just mentioned that QUIC is QUIC is almost there. It's there, actually. You've seen that the RFC is finalized, but it's almost there since we have to wait for support in browsers in all the languages. So it's almost there. You've seen that implementing QUIC and using QUIC with Netty is challenging since it's in incubator still, and it's just Netty API is somewhat complex and not designed for just normal day-to-day development. On the other hand, we've seen that Reactor Netty is tailored for really good user-friendly API, and it's designed to provide better Netty experience. And we've seen that Reactive is even better with RSocket, and it's even better with QUIC, since with RSocket API and with RSocket Design and with RSocket model, we haven't changed anything related to our API. And this is really important, since our API and our users doesn't have to break anything in their applications. They still can continue using RSocket fluxes and monos, and that's it. With that, use RSocket to make your life easier. With that, thank you, folks. And if you have any questions, please ask them in the chat. Or if you wanna learn about RSocket Reactor Netty, please visit Project Reactor/Reactor Netty. Or if you want to learn and see how QUIC is implemented in RSocket, just visit RSocket at GitHub/RSocket Java, and you're gonna see the first bits of this implementation and support. So thanks everyone for being with us.
Yeah, if you have questions, there is a question tab for Q&A, so just ask there, and we can stay here and answer your questions. So only I do not see.
Yeah,
Yes,
looks like.
Thanks a lot for the comments. Yeah, there is a lot of stuff that we can show you. Unfortunately, the time is limited, so we tried to summarize only the basic things. I do not see any questions, so yeah, you can reach us on the Reactive Netty support channels and RSocket support channels at any time. So if you need more information about the content that you saw today, just don't hesitate and contact us.
Okay, looks like we don't have any other questions, so we can just end up. Enjoy the rest of our evening.
Yeah, enjoy the conference, and yeah, have a nice day, evening, afternoon. Yeah, thank you, and bye-bye.
Bye, everyone.